Today we'll be talking about waves, and then we might do some demonstration on waves. We want to understand what waves is all about, but we have to start with the basics, which is spring. And if I may ask, can you name one product that is made of a spring? Any product you know that has a spring? Else?
Suspension on your cars.
Pen? Yes?
Suspension on the wheels.
Very good. These are some products that are made of spring, and there's a purpose for that. Here in this class, I can see one other product that is made of a spring. Pens like this is a pen. If you press it, it brings out this. However, if you open it, there's a spring right there. So there's a purpose for that. And that's what we are going to look at today. Right now, spring and vibration has something to do with waves. And waves, there are different forms of waves, like mechanical waves and electromagnetic waves. The electromagnetic waves you use it every day in your cell phone and television. However, some of the mechanical waves we are going to be talking about today, so that we'll have a grip of what waves and vibration is all about. Now, to enable us understand this concept very well, we have to do some reading right here in the class, at home, in the library, everywhere. Now, to do this reading, of course, you have your recommended class test, which I believe everyone has. But that's by the way. There are other books or tests that can give you an idea of what vibrations and waves is all about. This is one of them. We're going to do some exercise from this book. There are other articles too, which you can read to have a good idea of what waves and vibration is all about. This will be one of them. This is a geophysical newsletter. There is this magazine. It has information about physics. So if you have any way you can get some of these books, just open them up, read about the articles, connect it with what you're learning, and then you will find it very useful. Meanwhile, there's another book. This one is by me, and it contains several projects that I did as part of my capstone when I was graduating, and that was several years ago. So I will open one of the pages, and then right now, let's go to the springs. If you look at it in a stable position, if you attach any weight right here, it's going to move from the stable position, and then it will start moving back and forth, and that is vibration. There's a special type of vibration this thing is happening. If you leave it without stopping it, it will go forever, it will never stop. However, one of the reasons why it will stop at some point is because of air friction. Because of air friction, it will stop at some point. However, if you just leave it without any air friction, it will continue vibrating unstoppable. If you do the same thing on a flat surface, attach it the same way on a flat surface, and release it, it will keep moving back and forth. However, due to the frictional force between the flat surface and the spring, and then the mass is going to stop at a certain point. Now, we are going to do some theories behind this. You have your spring original position. Then when you attach a mass on it, then it displaces with the mass. Depending on the mass of the mass, the displacement could be longer or shorter. The same thing happens if you compress this spring. Something is going to happen. A force will pull it down. So when you stretch it and when you compress it, a force will either try to bring it to the original position. And that original position is actually at the equilibrium position. However, this force is directly proportional to the displacement when an object is attached to it. Remember your Newton's second law of motion, which is equal to what? Equal to what? Yes, and that is mass times acceleration due to gravity. Now, in this case, whenever you have a mass acting towards the gravity, you have a force. But in this case, for a spring, there is a force that returns it back to its original position. And that force is called restoring force. Restoring force. It's just like to restore something, to bring it back. Now, this restoring force is opposite to the direction of the applied force, which means if the applied force is coming this way, the restoring force is going the other way. Does that make sense? If you don't understand, please ask me. So now, this very force, F, is directly proportional to the displacement. Look at this original ruler. Then, when you measure again, you have this. So, original position is right here. Then, there's a displacement up to this point. You can represent it either by S to indicate displacement, or represent it by X to indicate displacement. It's the same thing. Now, this very restoring force is directly proportional to the displacement, S. So, when we talk about direct proportionality, what does that mean? Mathematically, arithmetically, direct proportionality. Yes?
It means that the same amount of force that it has is going to have the same amount of displacement.
Yeah, anyway, yeah, you are in the right direction. Any more ideas? It means the higher the force, the higher the displacement, basically. That's what it means. Do you know this? So, this is a graph representing some kind of relationship. So, when one quantity is increasing, the other one is also increasing. But with respect to spring, there is a condition, just one condition. That condition is provided that the elastic limit of the spring is not exceeded.